Thank you.
Assalamu alaikum. Today, inshallah, I hope yesterday we had good lectures, and I hope we had some nice conversations. Today, inshallah, we will continue what we started yesterday, and I hope it will be fruitful for any one of us. Thank you very much. Let's start. Today, inshallah, I'll talk about another topic, which is absorption. Of course, everybody knows what's absorption. Absorption is very important technique for water purification. I think you know that there are many techniques used for water purification, like absorption, like photodegradation, like filtration, and several techniques. One of these most important and the easiest ways for water purification is absorption. Let's talk about it, and just this slide talk about very important and also known definitions, which is what's adsorbate and what's absorbent, what's solute and what's solvent. The adsorbate of of course, it is a substance being absorbed, which is either gas or something in liquid, and adsorbent, which is a material which makes absorption or takes this fluid, which gas or liquid, to its surface. Solute, of course, solute and solvent are well known, which is bigger amount, which is lower amount. The bigger amount is solvent, and lower amount is solute. But what about there is very important or very fundamental expression, which is absorption. Absorption means everything about taking these materials from fluids, liquid or gas, to the surface. This is absorption. But if we divide adsorption, there is absorption is some, if you take the amount of, if you take the solute or the material to the surface, this of course it is being adsorption, and if it's in the bulk it will be absorption. Like if you have a piece of a chalk in water, just it will be on the surface, this is adsorption. But if it use sponge, it will be absorption. This is fundamental. And what about the absorption? Absorption is divided into two parts or two types, which is physical absorption and the chemical absorption. Of course, we should know what is the difference between chemical absorption and the physical absorption. The main, of course, this is how it looks like. This is physical absorption. I think you know. Now, both of them, it has differences. Please let me tell you briefly what is the main difference between physical absorption and the chemical absorption. The main difference, which causes all the other differences, is forming a bond, chemical bond between the adsorbate or the gas and the solid. In chemical absorption, there is a chemical bond. However, in physical absorption, there is no chemical bond, just condensation of the molecules together on the surface of the solid, and forms a multi-layer of these gas molecules on the surface. This means the main difference, which causes all the other differences, if you count the differences between them, 1, 2, 3, 4, 5, 6, all of them, the origin of this difference is the formation of chemical bond between gas material or fluid and the solid. And this is brief the listing of the difference between physical absorption and the chemical absorption. The force in physical absorption, just like condensation, and in chemical absorption, it's a formation of chemical bond. Chemical bond means, I am sure you know, formation of chemical bonds is followed by releasing energy or absorption of energy. Formation of chemical bonds. Any reaction, it should have two stages of energy absorption and desorption, release and absorption of energy, and also release of some energy. The breaking of bonds is always followed by absorption of some energy, and formation of bonds is always followed by release of some energy. In chemical absorption, there is a chemical bond is formed, and release of energy becomes after. Here is the absorption, heat of absorption. In physical absorption, it is very small because there is no chemical bond is formed. But in chemical absorption, there is a large amount of energy is released because it's a chemical bond is formed. In the number of layers for physical absorption is one or multiple layers, but in chemical absorption it's only one layer, because the formation of bond is only between the first layer and the surface. But in physical absorption it's only condensation, because if you make the first layer condensation like this in here, in this one, the first layer condensation between the molecules of the gas and the surface. However, after that, condensation between the second layer and the first layer, and the third layer is condensed on the second layer, and so on. Let's turn back here. Dependence of gas and the solid. Of course, if you make reaction, this means that the reaction depends on both reactants. Here, the gas and the surface are, please consider it as two reactants. Then it will depend on the formation of chemical absorption, will depend on both of them. However, in physical absorption, it will not depend on both of them. Okay. How fast? Of course, in physical absorption is rapid, but in chemical absorption, which is formation of chemical bond, little bit slow. In physical absorption, of course, there is condensation and evaporation, while in chemical absorption, just formation of chemical bond, and that's it, until you break this bond with some energy. And I'd like to show you with related to the formation of the chemical bond. Of course, as I just mentioned now, the formation of chemical bond should be followed by the release of some energy. This energy is the heat of absorption. This means the heat of absorption is exothermic or endothermic. It should be exothermic. Let's check if it is exothermic or endothermic. Heat of absorption is, here I want to tell you another point is, how can we determine the heat of absorption? The heat of absorption is determined by, the heat of absorption is determined by, heat of absorption is the evolved energy, okay? But if we break the heat of absorption is released, is the released amount of energy. Okay, let's check if it is endothermic or ectothermic. Of course, you know this is delta G equals delta H minus T delta S. Of course, delta S after absorption, is it positive or negative? Should be negative. And delta G, of course, if it's a spontaneous process, then delta G will be negative as well. So delta H is negative. So delta H is a negative value because it's summation between summation of delta G negative value and delta S T delta S is a negative value. This is so it is surely exothermic reaction. How can we calculate it? Let's see. Delta G, yes, that's what we just mentioned now. Delta G is negative and delta S is negative. So we calculated by Clausius equilibrium equation, ln P2 over ln P1 equals Q, which is delta H, heat of absorption divided by R. R, of course, you know, it is a universal gas constant. It has 3 values, and we will mention about it soon, inshallah. P2 at T2, P1 at T1. If we have some data, I will show you. Of course, we can replace Q by delta H, and K, the rate of absorption, with P, it's the same to have these equations. If we have an example, when hydrogen absorption on tungsten powder with coverage of theta equals 0.1, it was noted that hydrogen pressure was 3.06 kilopascal at 600 degrees C, and it was 6.6 kilopascal at 700 degrees C. Calculate the heat of absorption in this temperature range. Of course, it's very easy. It's direct calculations or compensation. Ln P2 over P1 equals Q by R, T2 minus T1 over T2 T1. Of course, you know, in thermodynamics, you should use T as Kelvin, but only you can use it in Kelvin or Celsius in subtraction only, okay? But in multiplication or other other mathematical process, you should use it in Kelvin. In this case, we should use it in Kelvin. We will transfer 600 or make it from degree C to Kelvin, as you can see here. And we used the R value 1.9. What will be the unit of Q? What will be the unit of Q if we use this R value equal 1.987? This means Q should be with the same unit. If we use R equals 8.2, which is joule, so Q should be in joule. And this value is in calorie mole calorie for every calorie over mole Kelvin. Then Q should be in calorie in this equation. We just substitute and make it like this. Q, we will have Q value, which is delta H equals 28.5 kilocalorie per mole. Then we could calculate the delta H in this example. And I have a little advice for you. Of course, in each exercise or in each problem, you can get, it's like a small story. Just imagine we add something to something, we divide something, we took something. It's small story. So each part of this story should be useful. The writer doesn't add it just haphazard. But in this case, it will not be a problem for us if the equation we will use is ln P2 over ln P1 equals Q by R T2 minus T1 over T2 T1. Does this equation has any information about theta or not? It doesn't have any information about theta. This means we will not use this information. But we added this information, but it is for to distract you, okay? So you will not use it. So don't be distracted. Just focus on your equation and substitute these values, and you will get delta H finally. We have other problems like this. We can just forward to you, and you can try by yourself if you have, inshallah, I am sure you have the ability to solve these problems, to calculate the delta H of these reactions. Any thing or any process or any phenomenon should have some factors affect this phenomenon. Okay, some things that increase absorption and other parameters which decrease absorption. The factors affecting absorption process of gases on solids are as follows. Number one, the nature of adsorbent. Nature of adsorbent, the nature of the solid material. The solid material, what is its nature? Number one, about surface area. Of course, you know the surface area. Once the surface area is high, the absorption will increase. If surface area is low, absorption will decrease. And polarity. Polarity is a very important as well. A nature of adsorbate, like liquefaction and polarity, and temperature of the absorption medium, the temperature, and also the pressure of the adsorbed gases. Let's take one by one as follows. For example, about surface area. Of course, the increase of surface area means increase of active sites that can make absorption, which leads to increase of absorption, the amount absorbed of the gas on the solid surface. Why? Of course, just mentioned that the increase of surface area leads to an increase of absorbing sites. So finally, divided solids and some porous substances are good absorbents. Why? Finally divided means if we go from bulk material to divide to nanomaterials, that means I increase the surface area. That means I increase the availability or the available sites to make absorption. And also porosity. Porosity means the presence of some pores on the surface of the material makes it it's just not because it's porous, but because this porosity increases the surface area. Like if you remember the sponge we just showed some time before, it has a lot of pores. This means its surface area is very high. If it's just blocked everywhere, then it will have a very low surface area. Of course, if we are sitting in a hole like this, surface area will be like this. These are the sites that can accommodate students. And if it is small, but if it is very large like this, it will have much more students and absorption will be better. The other factor for nature of adsorbate is the liquefaction. Liquefaction means is the transformation of or change of gases to liquids. This is liquefaction. If liquefaction, as we mentioned before, that physical absorption is a kind of liquefaction, is a kind of van der Waals forces between the adsorbate and the adsorbent. So if the material of the gas is easily liquefied, like ammonia, HCl, Cl2, CO2, then its absorption will be higher. If it is permanent gases like oxygen, nitrogen, hydrogen, then its absorption will be very low, or its absorption will be very small or very little. It will need very low temperature to make absorption, because when it transfers from gas to solid, this means I am trying to condensate these molecules to the surface. Condensation means liquefaction. Okay, so if the condensation of this of NH3 HCl is easy, this means its condensation is easy, liquefaction is easy, and the absorption is better. But if the other gases like oxygen, hydrogen, liquefaction is difficult, condensation is difficult, and the absorption is difficult. Finally, we will talk about polarity. Polarity means the formation of charges on the surface of the adsorbate and the adsorbent. These charges make it, of course, you know, plus is attracted to minus, minus is attracted to plus. Okay, this means the polarity makes it easy to make absorption if they both are polar surface. And I just want to remind you that there is a very nice and fundamental in dissolving materials. They were always saying polar dissolve polar or like dissolve like. This means polar things are attracted to each other and the non-polar materials are attracted to each other. If you want to dissolve an aromatic material, you should go to non-polar solvents. If you want to dissolve inorganic material, which is ionic, you should go to, like NaCl, for example, you should go to water, which is polar. But if you take this NaCl to, for example, diesel or petrol, like benzene, it will not dissolve. And I think there is a very nice quote in Arabic in that الطيور على أشكالها تقع, that the birds are going to its similar. It is the same meaning. The final is the concentration or the pressure of the gas, concentration of solution of solute in solution, and the pressure of the gas. If this concentration is high, the absorption will be high, and vice versa until saturation. This is how the pressure goes at very low pressure, or an increase in the pressure leads to an increase in the amount absorbed. More increase leads to increase of the amount absorbed until the rate will be lower, and then a parabola or saturation will occur at the end. And the second is temperature, and the third is temperature. We adsorbate and the adsorbent and the temperature. Temperature, of course, it is, as we mentioned several times yesterday and today, it's a product of the reaction or a reactant. Temperature, if we increase temperature, what will happen? If we have condensation, for example, of nitrogen, NH3 over a solid, what will happen? If we increase temperature, will NH3 will be dissolved or not? It will be dissolved or not? It will not be dissolved. This means increasing the temperature will lead to decrease the amount absorbed of the fluid on the solid surface. And this is very simple example that if we have nitrogen at 273, which is 0, only 10 centimeter is absorbed of nitrogen in the solid. And if we decrease temperature, the amount absorbed will be higher, and so on. And if we decrease temperature more, the amount absorbed will be higher. And this is a very simple graph showing that the amount adsorbed decrease by increasing the temperature. Of course, this is a small or minute explanation why decreasing the temperature leads to increasing the amount absorbed and vice versa, because absorption is exothermic, and if we add temperature, this means it will go to the other direction, according to Le Chatelier. This is a very simple experiment that we add adsorbate on, we add gas on decrease with it increases temperature. This when we add the material at 0 degrees C, its amount adsorbed very high, and if we increase temperature, the amount adsorbed becomes lower and lower and lower after increasing the temperature. Effect of polarity of solvent and adsorbate. The polarity is very important as well, because there is also another very nice experiment. We took butyric acid, propionic acid, and acetic acid. All of these are aliphatic acids which has different molecular weights. If we add these acids to different solids and the different solvents, we can see the experiment. It will be like this. Adding aliphatic acids to toluene solvent. Toluene is non-polar. over silica, the acetic acid will be easier to be absorbed and higher absorption because it is the lowest molecular weight. But in case of using water as solvent, which is polar, over carbon, which is non-polar, the butyric acid higher molecular weight will be better in absorption. So absorption depends on the surface polarity and the surface and also the solvent and the molecular weight, because the polarity affects very much in absorption process. As we just mentioned, polar dissolve polar, like dissolve like. It is the same. It is the same basic of the same principle. Now we will go to the two very important theories that explain the absorption, which is the first one is the Langmuir absorption theory. This is the most important theory for in chemistry, not in chemistry, in catalysis, because Langmuir discussed the chemical absorption, and the chemical absorption is the main idea of heterogeneous catalysis. So please try to focus on this theory because it's very important. Before adding this theory, of course, you know, there is nothing ideal. That means if you just say a rule, any rule, you have to minimize the effect of some factors to get it easy for calculations. Now he tried to minimize some factors or neglect some factors. So he added some assumptions. What are the assumptions of Langmuir? Number one, gas form only one layer. So he didn't like to make a headache. Only one layer, to just neglect the other the effect of second layer or third layer. So just to minute the error. That's all. But we can't say it is not formed. It is he assumed that it is only one layer. Next is, at a given temperature, a dynamic equilibrium must be attained. Dynamic equilibrium means there is an equilibrium, means there is absorption and desorption, like this. 1, 2, and 4 are absorbed, 3 and 5 are not absorbed. Then equilibrium occurs. Other two, you can see only 2 left the surface, desorbed, and the other 2 was absorbed in the surface. So there is a dynamic equilibrium. Dynamic equilibrium. It is not static equilibrium. Dynamic equilibrium means absorption occurs and desorption, absorption and desorption, and so on. The third assumption is he assumed that the solid is perfect, homogeneous. And also I assume that it is not true 100%, because there is no perfect surface. There is no perfect surface, okay? He assumed that the surface is perfectly homogeneous like this. However, he assumed this kinks and edges and all the other things are not there, but it is not completely true. And he also assumes that the interaction between absorbed molecules is assumed to be negligible. This means these particles are very close to each other, but they don't interact. This means each one of them is alone. He doesn't want to interact or just hit or collide with the others. Just sleep alone. Number 5, the heat of absorption is therefore independent on coverage. That means delta H is independent on theta. Coverage means the surface, as you can see here, the first one, the surface here, this one, the surface, if the surface is covered completely, this is theta equal 1. And if theta independent on theta, this means whatever the amount of theta or the coverage of theta, the delta H doesn't change. He assumed like this. He assumed this. This is the surface, and these are the molecules. They are adsorbed, and like this. All the surface is similar. all these particles don't interact to each other. All these particles, there are some kind of some kind of dynamic equilibrium, and he assumed that all the surface is one unity, and the surface is the covered surface is theta, and the uncovered is 1 minus theta. So it is known that the amount of course, the absorption process increases when the surface is empty. So if 1 minus theta is large surface, the absorption process will be higher. If theta increase, the amount of absorption or the rate of absorption will be low. We will see this in this slide. The covered surface is theta, and then the uncovered surface is 1 minus theta. The rate of absorption is proportional to the pressure of the gas and the surface which is not covered. If the surface is if the uncovered surface is large, this means a lot of absorption will occur. And if the P is great, if P high, this absorption is higher. Then the rate of absorption depends on P and 1 minus theta. And the rate of desorption, then the rate of absorption, of course, we will remove proportionality sign and equals K1 P 1 minus theta. This is the rate of absorption. And the rate of desorption is proportional to theta. Then the rate of desorption equals K2 by theta. At dynamic equilibrium, the rate of absorption is the same as the rate of desorption, like this. The rate of absorption is the same as rate of desorption. If this is equals this, if K1 P 1 minus theta equals K2 theta, then at this time K1 P minus K, just make it more simple and more simple, and then more simple. It's the same equation, just multiply and subtract. It's the same. Then finally we get this equation, which is theta equals K1 P over K2 plus K1 P. Just we also make some kind of rearrangement. We abbreviate it like this. If we assume B equals K1 over K2, this is very easy, no problem. Theta equals B by multiplied by P over 1 plus B multiplied by P. In this equation, I'll just tell you very small thing. If you have million rupees, please pray for me to have million rupees. If you have million rupees and I just give you one rupee, and I tell you, somebody will tell you how much rupees you have, how much will you say? What is the number you will say? You will say 1,000,001 or only? Of course, this is a very this is assumption that theta, if theta equals to V over Vm, theta is the amount, is the covered surface. V is the amount already on the surface of the gas already on the surface. Vm is the monolayer, the amount of gas which can cover monolayer of the surface. Okay, theta equals V over Vm, and we can just substitute instead of theta. We add V over Vm, and we can get, this is very simple mathematics. P over V equals 1 over Vmb plus P over Vm. This is the linear form of Langmuir equation. In this equation, we just make a plot between P over V and P. At this time, the slope will be 1 over Vm, and the intercept is 1 over Vmb. Okay. And this is and we can sometimes when you make absorption process or absorption experiment, they ask you which is it belongs to Langmuir equation or Friendlich or Tinkin or. If it gives straight line, then it follows or it is due to or we can apply Langmuir equation on this adsorption process. And of course, slope. The slope is 1 over v, just we mentioned right now, and 1 over vmv is the intercept. Vm means you can see this the amount of the gas, the amount of molecules, the amount of gas, or the amount absorbed, which can cover one monolayer of the surface, all the surface. So, what is the reason? Why can we do like this, or why can we? What will we use this? Simply, if I ask you to calculate the surface area of this material, surface area of this material. Now, and I give you the surface area which is covered by one molecule. Simply, you can say that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 by, for example, 2 centimeters, then this will equal 24 centimeters, right? Right. Here, we can use this to calculate the surface area. If we calculate Vm and we just make small calculations, and we will get to know the surface area of this material. And to know surface area is very important to study some many parameters, as we can see in future, inshallah, in another lecture. Of course, in this hole, it has some blocks like this. If you count how many pieces like this, and you know the surface area of each one, you multiply and you can get the surface area of the material. So we can use Langmuir isotherm or Langmuir equation to calculate the surface area of solid materials, like as I'll tell you. If we calculate Vm, this means if we divide to 22.4 liter for 1 mole, then we will get to know the number of moles. And from number of moles, if we multiply by Avogadro's number, we will get to know number of molecules. And if we get number of molecules, if we multiply by sigma, which is the area of one molecule, this is the number of molecules. If we multiply by the surface area of one molecule, then we will get to know the surface area of all the material. And then if we divide by its weight, then we will get to know the specific surface area, I mean, for 1 gram. I just wrote it like this. It is very nice. If this is the number of moles, V, which is the amount adsorbed, the volume adsorbed on monolayer, divide by 22/400 gives number of moles. And if this is the number of molecules, if we multiply number of moles by N, which is Avogadro's number, it will give number of molecules. And if we multiply number of molecules with the surface area of one molecule, it will give total surface area. And if we divide by weight of the solid material, it will give specific surface area, which is surface area per 1 gram. And this is this equation we can simply change N by its value. And the sigma, if we use sigma for nitrogen, it is known as well. We can just add it, and we can use this equation and calculate the surface area of a substance. So from Langmuir, we could calculate the surface area by knowing Vm of the material. And this is a simple example as well. Please read it. The volume of nitrogen gas at 1 atmosphere and 273 K required to cover 1 gram of the silica gel is 0.129 decimeter cube. Do you know what is decimeter cube? Decimeter cube. Calculate the surface area of the gel if each nitrogen molecule occupies an area of what 16.2 something meter square. This is the surface area of covered by one molecule of nitrogen. Of course, it's direct substitution, and you can just see it. It's very easy. You divide the number of the volume over 22.4 equals something in moles. Number of moles by Avogadro's number, it will give something of molecule, and the number of molecules it will, by 16.2, which is a surface covered by one molecule of nitrogen. It will give total surface area, as we can see. This is another example. This example you will meet for sure in your work when you can when he gives you some data and he asks you directly, is it follows Langemeyer equation or not? I am sure if you read some papers or if you just go to any lab and make some absorption, he will ask you this question. The following data were recorded after absorption of carbon dioxide on 1 gram or charcoal at 25 degrees C. Prove that these data follow Langemeyer isotherm and calculate Vm and the surface area of the charcoal. The cross section of area of CO2 is 19 angstrom. Of course, 19 angstrom square. P equals gives you different values of P and gives you the volume Vm at different the volume at different P's values. So this is P, this is V, and then to apply Langemeyer, we just divide P over V. It's like this, like in this table, and then plot P against P over V like this. It gives you straight line. The slope is, if you remember, the slope is 1 over slope is the Vm equals 111 milliliter. At this time, if you know the Vm, you can just apply in the equation just in previous slide. It will and substitute sigma and the Vm and the mass. The mass is 1 gram. Okay. So surface area will be 567 meters square per gram. So first question, he asked you to prove it is follows Langemeyer equation or not. If it gives you straight line like this, which is this one, if it gives you straight line, this means it follows Langemeyer isotherm. If it doesn't give you straight line, then it doesn't follow Langemeyer isotherm, and you just check another equation. And this is Vm, the second demand he asked us, and the last is to calculate surface area, and we did. Is it clear? Any problem? Now this is another example, and another example we will also transfer to you, and you can try by yourself. We just talked about chemical absorption. I'd like to ask you a very simple question. What is the main difference between physical and chemical absorption? Excuse me? Excuse me? It's multi-layer. Multi-layer. I just said there is one big difference between them, and beyond this difference, all the other differences are coming. The main difference between them is the formation of chemical bond. Okay. After that, formation of chemical, because the formation of chemical bond means that in the first layer, if it forms chemical bond with the surface, this means the second layer will not find the surface to do so, it will be monolayer. But if it's just condensation, so condensation, another condensation, because there is no bond, it is just condensation. And you can make condensation on the wall or the glass or wood, condensation will happen, whatever it is. But if you make, if you want to paint, for example, in this color, you can't do it on the wall, but you just do it on the wood. Okay, so the main feature or the main difference between physical absorption and the chemical absorption is the formation of chemical bond. Here in Friendlich, he is talking about physical absorption. Physical absorption means multi-layer, multi-layer, multi-layer. No chemical bond, just multi-layer. And they use and these molecules are contacting to each other, and there is attraction between each other by van der Waals forces, which is very weak forces. That's why the heat of chemical absorption, heat of physical absorption is very small. Let's go to Friendlich. In Friendlich absorption isotherm, it is divided into 3 parts. The first part is at low pressure, and the absorption is going up very quickly because the surface is empty. And the second part, little bit intermediate pressure, which is intermediate rate of absorption. And the third part at high pressure, it is like a plateau, and it doesn't change with increasing the pressure. In these 3 parts or 3 regions, we will just tell you that at low pressure, the amount absorbed is depending on the pressure very fast. This may happen in the chemical absorption at the beginning very fast until it covers all the monolayer. And the W over M equals K by B. Okay, and at high pressure, very high pressure, you can see it is like a plateau. W over M is proportional to B naught. That means it doesn't depend on pressure. And at intermediate pressure, it is like this, and W over M is proportional to P over P to the power 1 over N. And in this region, Friendlich studied his equation. So we will take this equation to make it more, to explain about it, and just try to apply, treat it to get Friendlich equation. W over M is proportional to P over 1 to the power 1 over N. W over M equals K P 1 over N. If you can see, K is constant, of course, proportionality constant. P is the pressure gas absorption, and the N is constant. So K is constant, P is N is constant. N is very important constant because once you know N, and there is a kind of category, N equal has some values, and it determines the nature of the surface. And the W is the mass of gas absorbed, and the M is the absorbent mass. This is Friendlich. If we this is Friendlich equation. Of course, I will show you an example of Friendlich equation. But now, just let me show you what is the most application, or one of the most applications for absorption process is the chromatography. Chromatography is very important in analysis and in our research work, and also in medical science, and etc. 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 Because what is the main or the simplest idea of chromatography? Simply, it depends on the attraction between solute and the stationary phase of in chromatography. If you have a column like this, and you add stationary phase like alumina or silica or whatever, and you add different substances, mixture of substances, and you want to separate these substances. What will you do? Just add these substances like this, and add solvent. the solvent will take these materials to separate it. Do you know which force will derive these materials to move or to stop? Which force? The force which is deriving these materials to move or stop is the attraction between these materials and the stationary phase. Let me ask you, which will go faster? Those materials which has attraction, more attraction between stationary phase and these materials will remain, or it will go fast? It will. If attraction is high, this means it will stick and will move very slowly. And if the attraction is small, this means it will. It's like if you visit somebody who you don't like, just hello, bye bye. You don't like him, but if you like him, you want to stay with him sometime. You have a drink, you have a tea, and if he is generous, he will invite you for lunch, and chat, and etc. Okay, so you will stay more. You will stay more. Okay, but if you don't like him, just if attraction is in stationary between stationary phase and these materials is high, this means it will stay sometime. It will move very hard very slow. But if the attraction is very small, this means it will go very fast. This is chromatography. Of course, this is what I have just mentioned now. It has many types. Chromatography has many types. Let's in this if you check this picture, the upper one, which one has low attraction between the stationary phase and these materials? The red one has the least attraction. The yellow, and by this technique we can separate and analyze many of chemical materials, and this is how it works. I don't think it will. We will explain it here. If you have a sample, you just add the sample with on this column, and sample will go. And if you can see this is a mixture of solutes together. This is a mixture of solutes together. Okay. At the beginning, all of them are very close to each other. After that, after adding solvent, they started to separate like this, and adding more solvent, separation increases, and adding more solvent, then separation completed, until we can just this one will be drained here, and later the blue one will drained in another batch. And I think this is what I have just mentioned now. The less strongly absorbed compounds will concentrate further down the column in the order of their case of absorption. This is what I just mentioned now. And this is how it looks in laboratory sometimes. It is very compact here, and by time we can separate it. And I think we can say thank you very much. If anybody has any question, I am here. We can discuss about it. Okay, please.
As you said, in chemical absorption, there is only monolayer formation.
Yes.
And there is absorption of oxygen over metal surfaces, forming metal oxides.
Yes.
Layer by layer, it keeps on growing. So, isn't it an example of multi-layer chemical absorption?
Did I hear you correctly? That oxygen absorbed on metal oxides in different layers. So what is the problem?
Multi-layer.
Yeah. So it's physical absorption. By the way, physical absorption may be converted to chemical absorption. First, chemical absorption starts basically as physical absorption. Physical absorption occurs, and later the bond is formed. Once the bond is formed, then you will have chemical absorption. Do you understand? So if you have oxygen as multi-layer, so it's very simple to say that it is physical absorption. What is do you have a proof that it is chemical, and we just call it physical absorption? Once it's multi-layer means it made condensation. And I just mentioned in Langemeyer, the first item in Langemeyer, he says that the gas forms only one layer. I told you it is not completely right like this, but it happens some exceptions, not exceptions. It happens that some molecules may be absorbed as physical absorption. In the same time, there is a chemical absorption. So you can imagine that a part of the surface is physical and another part is chemical. It is not ideal as Langemeyer said. Okay, please. Okay, please. Thank you very much.
One of the problem that we have solved, lossless-Clapeyron equation.
Which one?
Lossless-Clapeyron equation.
Yes. This. Okay. Just wait. This one. Yes. Yes, please.
Sir, I think this equation has some mistake.
Which one?
ln P1 upon P2. ln P1 upon P2, not ln P1 upon P2.
This one.
Yes, sir. And in one problem, you have solved that the del H value is positive, that is endothermic process, which is not possible in general.
Excuse me, I don't catch you, please.
Okay, sir.
You are talking about this equation.
That equation is actually ln P1 upon P2, not ln P2 by ln P1.
Just wait. Just wait. This is, if you add ln P1 over P2, this will be here T1 minus T2.
Yes.
That's it.
Yes.
Do you understand?
But in one problem, you have answered that the del H value is positive. In the further
Delta H?
del H is positive in further slide, in numerical problem.
In here?
Yes, sir. Del H is positive, which is not correct, I think.
Yeah, I may have a mistake in the sign here. I'll correct it.
Clausius-Clapeyron.
I'll check it again. Okay? Okay. Please. Please, I'm listening.
My query is only for the students, sir. I know.
Okay. Thank you very much.
One more thing here is that.
Yes.
Is there any example of endothermic adsorption?
Endothermic absorption? For me, I didn't hear about it. But it may be there, it may be there. But for me, I didn't hear about it. My knowledge is that this process is exothermic process. If you have an example of endothermic process, please explain. No problem.
As I have studied,
Yes.
that in case of isomerization process, one compound is converted to another compound.
Yes.
The process is reversible, but the interaction between adsorbent and a metal catalyst, adsorbate and adsorbent, that process is very endothermic process, and that's why for the process to carried out, high temperature is required.
Yes.
According to Bantoff equation.
Thank you very much. Now you give me another information. Thank you.
One thing is this.
Yes.
Second thing is any deuteration process, that is one hydrogen atom is replaced by deuterium.
Yes.
So that process of interconversion is also endothermic process. These two are the very common example for
Okay, thank you very much. Thank you. Our friend just said that there are some examples that makes the absorption endothermic. Okay, but these examples, of course, there is a rule which may have exceptions. Okay, these are exceptions of the main rule, which is absorption is exothermic process because the formation of the bond. Okay, this is the main rule. But what my friend just said, it is exception of these rules. Okay, so but for our study, for our level, it is exothermic process. It may have some exceptions, yes, of course. Okay, thank you, brother. Thank you. Okay, thank you very much.
To kindly felicitate Sir by offering a floral, uh, by offering a sapling and a shawl as a token of respect. हाँ ये फोटोग्राफर है हमारे शॉल देना है मोमेंटम टॉप के बाद दे देते हैं So, I take this opportunity to introduce Professor Uzair Alam. Sir is currently working as a professor from School of Pharmaceutical Education and Research from Jamia Hamdard, New Delhi. And as all of us are aware, Jamia Hamdard it is a leading institution with NIRF rank 1 in pharmacy, and also it has a remarkable ranking in World QS ranking, that is 94 in the field of pharmacy and pharmacology. Professor Uzar's leading authority is in the field of pharmaceutical chemistry, and his group heads in medicinal chemistry and molecular modeling lab, where his groundbreaking research in drug discovery has garnered international acclaim. Sir was also selected as top 2% scientist by the list issued by Stanford University, USA in the year 2024. Professor Alam's primary focus is on combating diabetes and cancer. He is actively involved in computer aided drug discovery and molecular modeling methods, which find application in cancer treatment. And recognizing his outstanding contributions to the field, Sir has been awarded by various prestigious awards, which includes Young Scientist from Department of Science and Technology DST and SERB, that is Science and Engineering Research Board. His research is supported from grants both by ICMR and DST SERB, which has significantly advanced our understanding of these critical areas. Under Sir's guidance, there are 10 PhD research scholars who are currently engaged in current cutting edge projects that he directly supervises. And additionally, his academic career boasts over 1,000 academic research articles published in peer-reviewed journal with over 4,000 citations and a remarkable H index of around 40. With these words, I invite Professor Uzair to please continue with his talk entitled Biological Applications of Oxygen and Nitrogen Containing Heterocyclic Analog.
Uh, Thank you, ma'am, for the nice introductions. Good morning to everyone. So, today's title of this GIAN programs is Biological Applications of Oxygen and Nitrogen Containing Heterocyclic Analogs. So, I am not going to here, giving the detail about what kind of activity I am going to perform by cell line, in vitro assay, enzyme assay, or something. I'm here just going to discuss about because we have synthesized a lot of compounds, but until unless if you are not going to get the output in terms of bioactivity. So the docking is one of the tools, or dynamics, molecular docking, or in silico approach, one of the tools by which we are going to predict the activity of the design molecule, so that we can save our time in lab, or we can save our money as well as. So that's why we just have to synthesize a lot of compounds in the lab. If suppose we can get the 5 hits, 1 hit, so we can perform all the in vitro, in vivo, and cell line, everything we can get performed. So that's why here I'm going to talk today in terms of molecular dockings. And so how many of you have aware of this molecular docking? I think it's not new for all. Uh, so so here, so in protein ligand docking, basically I'm working in Schrodinger software since 2013 when I got DST Young Scientist, and that I've just purchased that software. So at that time, what I thought, what should I purchase so that I can enhance my knowledge? Because I saw at that time the research paper which were published from the south or anywhere in Elsevier on that thing. So I thought that whether what is these things is docking. In paper these images looks very good. So whether I am able to learn it or not. So for that, I can devote, 2 to 3 years to learn all these techniques of that molecular dockings and dynamics by this software. So I'm just giving the few of these slides, a few of my research and few of my case studies in this presentation, so that we can learn. And one more thing is that I can promise you within 2 or 3 days, I send one of my research scholar who is just going to, workshop, yeah, hands-on for 3 to 4 hours on Schrodinger software, where you can easily learn molecular dockings and dynamics, pharmacophore modeling, virtual screening, so all these techniques. So within, I just have to give up my words to Professor Raisuddin Saab. So in protein ligand docking, what we have to see, there's the two things in docking. One is called as the search algorithm. So here in search algorithm, we have to generate the large number of poses by the ligand in the binding site. Suppose if I am taking one molecule, so that molecule have so many chiral center, they have the different orientation. If somebody who is sitting in that chair, so sometime what happen, I'm having sitting in this way, that way, in what pose I'm just getting. So I just have the different way to sit in the chair. The chair is the same, okay, but the way I'm just sitting, it may be the different from other. So that's why in case of search algorithm, we have to generate large number of, ये इसमें लगाना पड़ेगा रईस भाई ये चीज ठीक ये देखिए कौन सा किधर है बताइए हाँ वो अच्छा 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 ये पॉइंटर है ना अच्छा इस पे पॉइंटर नहीं आ रहा ना,
पॉइंटर सर इस पे नहीं आया,
नहीं आता है ना?
वो आएगा जी, नहीं आएगा
ओ
सर, वो नहीं
अच्छा
आएगा,
अच्छा 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 नहीं आया, ठीक ठीक,
ठीक नहीं, वो उसका जो इंटरप्ले
अच्छा 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 ठीक ठीक. So here I am taking one of the compound from chicory plant. So here this is the structures of chicory acid. So as I see, this chicory acid have dihedral angle, torsional angle. So they have to change their, I mean, shape or orientation by change their dihedral angle, by change their, I mean, torsional angle. So they have to generate the large number of, I mean, conformers. So you can see here I'm just taking 9 of these most stable conformer, and these conformer are just going to be, I mean, these were the ligands which were going to bind with that of the protein. So this is the target site of the protein, or you can say the binding type site. So in docking, there is an interaction of two molecules. One is called as the small molecule, another is called as the large molecule या macromolecule, that is called as the protein, that is called as the protein or receptor. So here you can see the chicory acid, they have to form a different shape by changing their dihedral angle, by changing their torsional angle. So here this is the binding site, and this may be one conformer, may this be this way, that way. So there are different poses which actually going to bind on the active sites of the binding sites of the. So here I am taking, this is the protein of the alpha glucosidase. Alpha glucosidase is the one of the major target for the development of anti-diabetic agents. So there are a lot of anti-diabetic targets. What? SGLT2, DPP4, GLP1 agonist, PPR gamma. So alpha amylase, alpha glucosidase. So here I am taking the large, I mean, protein that is called as the alpha glucosidase. So here we just going to put the ligand into the binding sites of the alpha amylase for the. So now, so first thing we have to see the search algorithm. The first thing is that search algorithm, and second thing is that scoring function. So what do you mean by scoring function? Because once the ligand interact with the receptor, they may just have, they have to form certain type of interaction that is called as the non-covalent interaction. It may be the hydrogen bonding, it may be the van der Waals interaction, it may be the pi-pi interaction, it may be the pi-cation interaction. So here basically in docking we have to find out the binding affinity of particular ligand for the particular target site or protein or the receptor. So how we have to say that our ligand molecule have less affinity or high affinity? So for that we must have some scoring function or some energy in the form of kilocalorie per mole. So here in the binding affinity is sum of the van der Waals force energy, electrostatic, hydrophobic and hydrogen bonding. So basically here we have to calculate the interaction energy between the ligand and the receptor. If your ligand is more stable at the binding site, so that means which we have. So scoring function basically we have taken in form of negative. So suppose one ligand have the two conformer, one having the minus 10 kilocalorie per mole, another having the minus 8 kilocalorie mole. Which one is the high energy? Which score we have taken for minus 10 or minus 8? Minus 10, because minus 10 is the less energy, and less energy means more stable at the binding site. So here, and one more thing is that in Schrödinger there are the three way by which we have to perform the molecular docking. One is called as the HTVS, high throughput virtual screening. Second is called as the standard precision, and X is called as the extra precision. So suppose if you have a 1 lakh millions of the molecule, so you are not going to perform the extra precision docking, because here you need to have to run one ligand molecule for docking. It required 2 to 3 minutes. So it's not possible to, I mean, dock the millions of compound through the virtual screening. So for that, initially we have to get through the HTVS. But one more thing is that one you have to get the large number and you use the, speed is high, but accuracy is less. So accuracy is more in case of, extra precisional. So once you have to take in 10,000 molecule, after HTVS you got the 1,000, and after 1,000 through the SP you got the 50, and 50 you go for the extra precision, and finally you get the hit 2 or 3 molecule which have the good score or good binding. So here in docking, so here in molecular docking or ligand protein docking, two things is there. One is called as the search algorithm and the second is called as the scoring function. In case of search algorithm, what we see? We have to find the different conformers of, we have to generate the different conformers from the ligand by changing their dihedral angle or torsional angle. And each of these ligand, each of these conformer will have differently bind with that of their target site or the protein. So in docking, there are so many docking. One is called as the rigid docking, another is called as the flexible docking. Our protein is rigid or flexible? It is a rigid structure, but ligand may be the flexible or may be the rigid. How you have to introduce the rigidity? By incorporating certain double bond or something which are not going to rotate in their 3D space. That is called the rigidity. So most of our docking we can perform by the flexible docking. So in case of flexible docking, your receptor is, rigid docking, your receptor is rigid and ligand may be the flexible or may be the rigid. So on that. But there are some way, if you perform the rigid docking by some molecule, but you are not going to get the good output or enough output for activity. So in that case, you have to perform the induced fit docking. Your ligand is not properly going to interact with the receptor. In that case, what? You have to change the receptor orientation so that the molecule is going to interact the particular site. So here in case of induced fit docking, what we see, suppose I am taking hypothetically one molecule which having like catechol type of molecule. Here they have to make a van der Waals hydrogen bonding, and here they have to make a ionic interaction. So this is the receptor, this is the binding site, and maybe one of the amino acid or they have the free so C terminal which having the CO minus charge. Here this catecholamine, once it get accepted proton, it may be protonated charge. So they have to make a ionic interaction, they have to make a hydrogen bond, they have to make a van der Waals interaction. But the thing is that these molecules bind with the receptor by 3-point attachment, but 2 is very strong and 1 ionic interaction is very weak. So in that case, what happened? Receptor itself change their shape. Receptor itself change their shape so that the anionic carboxylate group get closer to that of the cationic amine, so that they have to form a strong interaction. So this is called as the induced fit. Induced fit is the term by which the receptor itself change their shape to accommodate the ligand for better interaction. This is called as the induced fit docking. Another docking they are called as the covalent docking. Suppose I am taking example of beta lactam like penicillin, ampicillin, amoxicillin, whatever they. So penicillin, so here there is a site that is called as the penicillin binding protein site. They have to make a ionic interaction with the lysine. They have to make a, here what happened? This pi bonds move here, this carbon become delta positive, this carbon become delta. So there is a one enzyme that is called as the transpeptidase. So transpeptidase are helped to make a cross linking with the NAM and NAG, so that the cell wall get grow and the bacteria will grow. So in transpeptidase, what happened? There is a serine residue, that is the amino acid, and serine having the free hydroxyl group, that is OH, and OH oxygen having the lone pair of electron which act as a nucleophile, and that nucleophile can attack on the electrophilic carbon. How these carbon become electrophilic? By moving the pi bond here. This is the delta negative, this is the delta positive. So once it get interact serine, so they are covalent. That means they are never detached from the, so this is called as the irreversible binding. In case of reversible, they are the short one. Once the activity get achieved, and after that the receptor get released from the ligand released from the receptor binding site. But in case of irreversible, in case of covalent bonding, there is no any ligand is detached till the new receptor is synthesized within the system or within the body. So this is called as the irreversible or covalent docking. So these are the types of docking, like rigid docking, induced fit docking, covalent docking. And so in Schrödinger, sometime, how many of you have to search the PDB ID in Google or something? Protein data, have you seen? Any of you? Raise the hand. So you have to search the PDB ID, suppose. And sometime what happened, you are not going to find any co-crystal structures. So in that case, how you have to perform the dock? Because once you have to remove the co-crystal from the binding site, then you are just going to impose your own ligand within the binding site, which can be occupied by your co-crystal. But if you don't have the protein which don't have the co-crystal ligand, what is the binding site you have to find out. So in Schrödinger, there is one tool that is called as the site map, or maybe some other tools in Schrödinger they are used, that is called as the homology modeling. In case of homology modeling or site map, when you don't have any co-crystal ligand. So in that case, how you have to find out the binding site? Because this is the whole protein. So in whole protein, how can you say that which is the binding point? It may be here, there, for. So for that, we have to perform the site map analysis to identify the binding site on if you don't have the information about the bound ligand on the protein structure, if you don't have the information about the binding pocket residue, you can identify to top rank. If you don't have to co-crystal ligand present in the binding site, to understand the binding site properties which can be used to lead optimization, use the 3D structures of target receptor to design or search potential drug compound that can be modulate the target function. So within 2 or 3 days, if I will send one of my research scholar, he can perform the site map analysis by Schrödinger, then you can able to understand properly what actually happened. So what happened, because once we have the protein, so if your ligand is going to bind with that protein, so how, because this is the structure, this is the ligand, and this is the whole protein structure. So in protein structure, some part is called as the hydrophobic area, some part they are called as the hydrophobic region, they are called as the ligand hydrogen bond acceptor region. This is the acceptor, and this is ligand hydrogen bond donor region. This is the green one, donor region. So here this one is the yellow one is called as the hydrophobic region. So if you have to find a protein where these hydrogen acceptor, donor, hydrophobic area, so in that case what happened, the ligand must have the, here is the acceptor, so ligand must have the donor. So if you see here this is the amino acid, here this is the N and H, and here is the nitrogen, that is the pyridine ring. So pyridine is what? They are hydrogen bond donor or acceptor. They are the acceptor because they don't have the hydrogen. But here this is the amino acid which are present in the binding sites of the protein. So this one is the hydrogen bond donor. So donor bind with the acceptor. Similarly here, if you see that's the hydrophobic, this is the phenyl ring, the benzyl oxy group is there. So this benzyl group is make as an hydrophobic part. So they have to cover up this yellow part of the hydrophobic binding site. So in site map analysis, how you have to perform? Once we have to run the site map, so there are, suppose in protein, we have to identify the 5 sites, 1, 2, 3, 4, 5. So how can you say that which site is the actual binding site? So on the basis of site score, D score, volume, size. So out of these 5 sites, which having the highest site score? 1.04, which means the D score. D score is the drugability score, which is, and volume, which is the large area. So out of 5, so here this one is the site 1, this is the site 2, site 3, site 4, and site 5. So here in site map 1, this is the binding area. This is the whole protein. I have taken the EGFR kinase protein. So here this part is called as the binding site. This part is the binding site. This part is the binding site. Here this is the 4th binding site, and this one is the 5th binding site. So out of 5th binding site, so this one is the actual binding sites of the EGFR protein. So on the basis of what? Site map score. So what is the site score? So site score, they have this equation 0.0733 square, and this one, and D score is the dragability, and binding site volume is in the A angstrom square, and here N is the number of site point, and E is the enclosure score, and P is called as the hydrophilic score. So here if D score, yeah, dragability score is more than 1, which is considered to be as an, in case of site 1, what is the D score? It is 1 point something. So if the D score is more than 1, then we have to consider. If the value is less than 0.6 or 0.7, we should not consider as a binding site. We should not be considered as a binding site. If the site score, dragability score is more than 1, so consider as a draggable site or the binding site. You can understand on what basis we can find out the binding site or binding pocket in the receptor or protein? On the basis of D score, site score, and D score and site score must be more than 1. And what is the criteria by which we are not consider if the D score or site score is less than 0.7 or 0.6? So now I am taking one examples of super oxide dismutase, or so many of you are working in the area of antioxidant. So antioxidant, how it can create? By generating of the free radical within the body. So like O2 minus dioxygen anion is the free radical, which is generate from either the oxygen or water or something. So there are some enzyme that is called as superoxide dismutase. This is called as the zinc magnesium copper catalyze enzyme, which converts what? Oxygen dianide into the hydrogen peroxide plus water, and hydrogen peroxide is further converted into oxygen with the presence of catalase enzyme. So our aim is here to convert the oxygen dianion, this is the free radical, into the hydrogen peroxide by superoxide dismutase, and hydrogen peroxide is further converted into the water and oxygen. So that's why free radical is just not going to, free radical is involved in for what? Cancer, inflammation, all kind of diseases or pathway, TNF alpha, interleukin, all they are been associated with that. So here, one protein PDB-ID, 2 JLP or 1 DGF. In that, there is a no co-crystals ligand is available. So how you have to dock in what area? So for that, we have to perform the site map analysis. So we, on the basis of D score, site score, I am taking only one site is here for catalase. So this is the copper zinc catalyze of the super D superoxide. So I'm not going to give the details of that. Similarly, in times of COVID, we just have to perform this SARS-CoV non-structures protein polymerase of 6 NRU. Even this, they don't have any binding site, so we have to perform the site 1 of this here. This is the white one, they are called as the site point. And this is the hydrogen acceptor, this is the donor, and yellow one is the, what they are called as the hydrophobic region. This is the whole proteins of SARS-CoV non-structures 12 polymerase. So I'm coming to later than first. So how many of you are in chemistry? All of you are from the chemistry background? Yes or not? So how you have to design your molecule? By hybrid designing, first of all, you go to the literature survey. Suppose if you are working on the pyrazole ring, if you are working on the pyrazolene ring, so you have to find the paper which, having the pyrazole containing EGFR activities there. So this is our design molecule, and this design molecule having the benzoyloxy, benzene, and this is called as the pyrazole ring. This is pyrazolene and dimethoxy, and this is the thiocarbamide. So in this, what happened? How we have to from the different literature, we have to find out the most potent molecule from the literature, and in all. So in case of EGFR kinase inhibitor, one thing is very important. There are 4 type of kinase: type 1, type 2, type 3, type 4. In case of type 1 EGFR kinase inhibitor, they basically occupy the ATP binding site. So this is the ATP binding site, this is the C terminal, and this is the N terminal. And the region which connect between the C terminal and N terminal, this region is called as the hinge region. In hinge region, there is one important amino acid that is called as the methionine 793. So which play a very crucial role for their bioactivity. So in all these, so they have to pick methionine 769, and our design molecule is also going to interact with the methionine 793. So this is the way, this is the approach by which we are going to design our molecule by searching the literatures, our own, desired molecule. Now, sorry, I have to explain these 2 slides already. Now, how we have to, suppose you have 2 compound. One is synthetic, another is called as the natural. So somebody who are working in the area of pharmaceutics, in the drug delivery or nano, so they basically combine 2 drug for making the nano to enhance the viability and all that. So here I am taking this work is under communication. So here I am taking one compound is selimarine, another is called as the epigallocatechin gallate, which is obtained from the tea extract. So how we have to perform the synergistic effect of these 2? Because if we could identify one binding site for one ligand, so we are not going to bind the another ligand at the same time, because the 2 compound having the different affinity. So we are only, because those who are having the high affinity, they can bind, and the next other one is replaced. So that's why what approach we have to apply to get the synergistic by docking. So in that case, we have to identify, one is the allosteric binding site, another is called as the ATP binding site in the same EGFR protein. So here you can see this is the ATP binding site, and this one is called as the allosteric binding. So at the same time, we have to perform the dock of the 2 compound. They have to give you the synergistic effect. So this is the whole protein of EGFR: chain A, chain B, chain C, chain D. So sometime we see, in the literature, many who have performed their activity. So 2 compound can be bind at the same binding pocket at the same time. How is it possible? Because one have the affinity high, another have the low affinity. So we cannot. So there are a lot of research who has been published in the reputed journal, especially in the pharmaceutics field area. They have to superimpose both the ligand at the same binding site, and they can show the affinity. So this is the wrong practice, did by the pharmaceutics or other person. So here, this is the epigallocatechin. This is the structures of epigallocatechins, which are represented into the stick form in the green, and this one is the turquoise color of silimarine. So you can see all these the binding residues of the binding sites. So this is the receptor view of that EGFR. Upper one is called as the allosteric binding site, and lower in is called as the ATP. what's called as the ATP binding sites. So you can see both the ligand is appropriately bind in a good pose. And this is the way by which we have to, how we can say that our own design ligand is actually showing the same binding pose with the co-crystal ligand present within that binding site. So for that, what we have to do? We just have to superimpose our own design ligand along with the co-crystal ligands of that particular ATP binding sites or the allostatic binding. So you can see the orientation and pose of our design ligand is same as that of the binding pose, and orientation of our design ligand is same as that of the co-crystal ligand. Similarly, in that same case of that superimposed dog pose of osimertative, osimertative is the co-crystal ligand, and here the ECG is called as the our own design epigallocatechin, the same methionine 793 and on that. And by molecular docking, how can you say that your molecule is ATP binding or type 1, type 2, type 3 or type 4? For type 1, there is a one called as the DGF motif. D for stand for aspartic acid, F for phenylalanine, and G for the glycine. So how can you say that your design molecule is type 1 or type 2 or ATP? So in that case, this is called as the side chain of aspartic acid in DGF motif points to the hinge region. This is called as the hinge region. Hinge region is the area which connect the C terminal and N terminal of the EGFR protein. So you can see the side chain of aspartic acid is facing toward the hinge region. So if this is facing toward the hinge region, means your DFG motif is in the inconformer, that is the type 1. And if this aspartic acid is facing away from that hinge region, in that case the DGF motif is the outconformer. Similarly, in case of side chain phenylalanine, which is away from the hinge region for the type 1, and for type 2 which is towards. So this is the way, this is the approach by which we can say our design molecule is the type 1 EGFR kinase inhibitor or ATP binding site. So before going to perform the molecular docking, we must have to first study about the whole protein structure. What are the activation loop, what is the phosphate loop, what is the alpha helix, what is the beta sheet, what is the catalytic loop, what is C lob, L lob, hinge region. We must have, and we just try to, what is the DGF motif, and we just try to dock with that particular ligand, because sometimes what happens, there are a lot of binding site. So recently few paper I have been identified where the researchers or scholars have performed the docking which is other than the binding site. So that's why earlier in case of site map analysis, first of all we must have to analyze or find out the exact binding site where actually we just have to perform the docking. So this is a site map or homology modeling if your co-crystal ligand is not available in that case. Similarly here, this is the most potent design compound 6H. So here they have to, for methionine 793, and they have to make it aspartic. So in docking there are two ways. One is called as the masterio, another is called as the glide. In case of glide, default is 2.5 angstrom, and in masterio that is 2.8 angstrom. So here I'm just within the software there is a flexibility of increase the interaction distance of between the ligand atoms and the interacting amino acid. So here 3.26 we can say this is the weak interaction, not because if your interaction is less than, distance is less than 2.8 or 2.5, you can say this is a strong interaction. But aspartic acid 1.17, this has the strong interaction is there. And we try to superimpose our adenine binding region here. Gefitinib is the co-crystal ligand of the particular EGFR. So you can see we just going to superimpose the gefitinib with that of our design molecule, and these two molecules, they have the same binding orientation, same binding pocket, and same amino acid interaction. So basically in docking we have to make a hypothesis that our design molecule is the best. So if you are not going to give you a strong hypothesis, how you have to present these all in the research paper? So if your ligand is missing all these amino acid and they are binding some other area, so how can you say that your work is, up to that mark? Not. So first of all, in molecular docking, you are not going to get only one PDB ID. You have to make whole, because during the COVID time, I have to generate 80 research star grids of DPP4, PPR gamma, EGFR, 80, 100. So during the data, I've just start running the system at my home, and every day I get the output. And before going to get the final result, we have to perform the dock of all that receptor grid. So how long we have to do it? Till the best results come out. So this is the way. But the student nowadays, what they do, they just giving the putting, find out one PDB ID from the literature and dock it. So this is not up to. So you have to perform your dock of your molecule by taking more than 10 or 15 PDB ID. And before going to get the PDB ID, resolution is good. And one thing is that if your design molecule is somehow structurally similar to that of that co-crystal ligands of that particular PDB, then we have to take out that only. And this is the molecular surface view. You can see the same way as. So in research paper, how you have to represent of your docking data, this is very important. Because this is the hypothetical thing, this is the computational thing. So you have to make a beautiful table where you have to make a different column, different rows, and in each rows you have to listed the list of compound, then the R group, docking score, binding free energy, so ligands of atom, amino acid, and there's the distance of interaction, pi cation, pi cation. You have to present all these data of the design molecule in this way. So this is the paper which is published in Archive der Pharmacie in 2023. Here, this is our design molecule. This is the quinoxolone compound, and here is the chloromenzine, and this one is the linker group, carbonyl NH and C double bond N. So this is our design molecule. So before going to perform the dock, what we have to do? First of all, from the literature, we have to find out what are those co-crystal, what are those reported molecule which have this fluoro or chlorophenyl ring, which have this quinoxaline ring or pyridine or something like this. So we have to perform the docking of one prototypic SB2358 bound to the P30 alpha MAP kinase. Similarly, on the right hand side, we have to perform by taking one ZL co-crystal structure. Here I am taking in the 1Y8 PDB1, 1YWR, and here also the pyrazolone ring. So what is the common thing with all these figures? So our molecule having the two hydrophobic moiety. One is occupied by hydrophobic pocket 1, another is by the hydrophobic pocket 2. So all I explain that all the kinase enzyme, they have the hinge region. So here hinge region, basically in case of EGFR, that was the methionine 793, or here in that hinge region, that is the methionine 109. So methionine 109, our design molecule, this is the co-crystal ligand. So we can say the orientation and binding pose of our design molecule is same as that of the co-crystals available in the literature. So this is the actual way to design our molecule. So you can see all the orientation of chlorofluorophenyl and phosphate binding site, hydrophobic 2 region 1, all that they are. So this is published in the Archive der Pharmacie. Now we have to, again we just have to find the dual pocket inhibition of sodium channel by lamotrigine. So lamotrigine is basically the anti-seizure or anti-convulsant drug which are present in just that pink stick model in the binding site of big sodium channel and the resveratrol. So nowadays resveratrol is one of the phytoconstituent most of the scientists who hardly left any area of activity. They just shown the, Alzheimer's, Parkinson's, anti-convulsant, anti-cancer, anti-diabetic, every work, every areas of research already been find out by the resveratrol. So here I'm just going to give this work is under communication. So here I'm just giving the, combination of resveratrol and lamotrigine, and we see the synergistic effect of these two drugs. So here we have to find out the two binding site. One is called as the site C, another is called as the site big. So in site big, lamotrigine having the high binding affinity, and in case of site C, resveratrol having the high binding affinity. So we have to dock these two drugs and the. So this is the resveratrol, here is the sodium. So basically they have to block the sodium channel. So if sodium channel is blocked, so what happened? Generation and propagation of the nerve impulse is not going to pass from one part to another part. So in case of local anesthetic or in case of so there is excessive neural firing in case of seizures or epilepsy. So how it can be overcome? By blocking the sodium channel, because sodium, calcium is one of the important cation which are responsible for generation of the action potential, depolarization, then partial repolarization, then of the repolarization by sodium, potassium and all that. So here we are going to block the sodium channel by the resveratrol, and we just have to inhibit the side big B by the lamotrigine. So we can get the synergistic effect in case of epilepsy. So anti-epileptic effect is enhanced by giving these two drugs in combination. One can inhibit the sodium channel, another can inhibit the side big of. So this is the two molecules in the same binding sites. One is the lamotrigine and here is the resveratrol. They are going to interact with the different amino acids. Now, this area, this work is already under communication. So again, the same work is there. Another target we have chosen, that is called as the GABA A site, GABA binding site. Already we know GABA is what? Pentameric. They have, made up of the 5 subunit, 2 alpha, 2 gamma and beta. So this is the electron biographic of that, electron cryography. So here we can see that gamma binding site, alpha 1, beta 1, and this is the gamma binding site. So this is the allosteric binding site of the GABA A. So what happened once your ligand is binding with that of the GABA A? So what happened, you can see the channel is just going to open up. So once the pore is open up, there is influx of the chloride. So once the influx of chloride ion, so what happened? That can leads to hyperpolarization, and that can hyperpolarization leads to decrease the neuronal firings, which are help in the epilepsy. So but what happened once your compound is absent in that binding site? So you can see there's the pore is closed or open? Pore is closed. So does it allow to pass the chloride? No. So there is no any hyperpolarization, no any decrease in the neuronal binding site, no any anti-epileptic activity can be achieved. So this is the way by which we are going to target the GABA A binding sites of that our resveratrol. So how you have to designing the COX-2 inhibitor? So COX-2, in case of COX-1 and COX-2, in computationally, how can you say that the COX-1 or COX-2? So there is some amino acid that is called as the isoleucine 523, and here in COX-2 that is called as the valine 2,3. So the molecule is big. So once we have to perform the dock at COX-1 site, so we cannot get any result of, because molecule are big and the COX binding sites, the binding sites of the bonding pockets of the COX-1 is very narrow or very small. So in that case, molecule cannot be accommodated because the isoleucine, they have the smaller and valine is the bulkier. They can allow the another bulky pocket will develop once the valence comes at 523. So here, this is the binding pockets of that This is the hydrophobic pocket 2, and this is the hydrophobic pocket 2. This is our own design molecule, and this is called as the selectivity pocket. So here the sulfonamide group is there. So they have to bind with that isoleucine, phenylalanine, arginine, histidine, serine. This is the selectivity pocket. This one is the hydrophobic pocket 2. This one is the hydrophobic 2. So here what happened during the design of our compound, we are going to introduce one flexible benzyloxy group. If you compare this molecule with the celecoxib, this is a well-known COX-2 inhibitor, and this pink color is the structures of the celecoxib. So, and this is the green color of our stick model, that is the design molecule, that is 5U. So what happened? So this benzyloxy groups come over to that of the phenyl ring, that is the sandwich type of structure. So that's why this area, so sandwich type of structure you can see is there. So you can see this part is in the sandwich type of structure. So this is the way we have to superimpose our design molecule with that of that our. So another benzyloxy group introduced in this molecule, the purpose is that they can occupy the hydrophobic pockets of the COX-2. So how you have to design the tubulin polymerization inhibitor? So tubulin is made up of what? Alpha subunit and the beta subunit. So alpha subunit is actually designed here represented in the purple color, and the yellow one is that of the beta chain. Beta chain, this is the alpha chain. In between this area is called as the colchicine binding pocket. So here there's the magnesium, GTP, all that. Our compound is actually binding with that of the colchicine binding site, and we have to superimpose this compound 5 with that colchicine binding site the same way as that. So this is the way we have to design our own molecule. Influence and steric means what? The shape and size. Sometimes bulky group, they are not making ideal interaction with the receptor and drug, and sometimes bulky group is also help the molecule to protect against certain degradation by beta lactamase or degradation by the MAO enzyme. So that's why it is very difficult to quantify the steric parameter, whether it is sometimes helpful, sometimes it is not bad for activity, sometimes good for activity. So it is very difficult to quantify. So this is the 2D QSAR. But in case of 3D QSAR, we have to generate the field, electrostatic field and the steric field. Okay, so suppose this is the whole room is there. So we have to divide it into a small grid or a small box is there. Each box have the different size. And now we have to identify one molecule with 3 or 4 pharmacophore is there. So we have to place that molecule within the grid box, and we have to start the grid box 0.1, 0.2, 0.3. And we have to take one probe atom that is called as the carbon, which have the plus charge. And now we have to move this plus charge carbon atom, probe atom near around the ligand's pharmacophore. And we can find out the steric effect as well as the electrostatic field effect. And then we have to tabulate it in the form of bioactive. So this is called as the 3D QSAR, that is the comparative molecular field analysis. We have to, generate the field around the molecule. Which area is good for activity, which area is bad, which is the green gene, blue region, that is actually we have to identify in that. So suppose we have taken one reference compound and 3 to 4 pharmacophore we have to put in that grid box, and after that we have taken 100 molecule, design molecule, and then we have to align all that molecule by keeping all the active pharmacophore. And now we have to taking each and every compound in that grid box, and we have to move that probe atom. I'm not doing this physically, the software did it. So they have to taking this probe atom near to that each of the atom, and we have to get the activity and field, electrostatic field or steric field. So this is called as the QSAR. So once we have to generate, then we can easily design or develop the molecule, which part we can keep in the molecule, which part which are not. So there is called as the partial least square method, PLS. So once we got is, so our molecule depends on the variables of the descriptors. So some is necessary for the activity, some is not necessary. So PLS method, what it do? It can reduce our variables, number of variable, so that what variable we have to keep, only those variables which directly depends on the biological activity, which directly depends on the, so this is called as the partial least square method, and that giving you the one equation by which you have to get this all. So this is the 3D QSUR. So we had to model C, then we have to just ligand based design drug, then design 5000 molecule, ligand preparation, protein preparation, receptor grid, then make a virtual screening of that. Already I have explained in case of so HTVS, it require 1 to 2 seconds for, and it will take 20 seconds, and it takes the 1 to 2 minutes for each ligands to dock. And after that, we get the 5 hits, then we have to perform the ADMET, then lead molecule, then binding energy, then we have to perform the molecular dynamics, then go for the in vitro and in vivo study. So this is the area, red area, what I said in 3D QSR, which part you have to keep for substituents, or which part is we are not going to add any substituent. That is all that contour map, steric contour map or electrostatic contour map. So somebody who are working in the area of natural chemistry or in that. So suppose I am taking one compound that is called as the Chicorium indicum, one plant. So from that we have to find out the 18 chemical constituents which are present in that Chicorium indicum. And we have to perform the virtual screening, and by taking that PDB ID 3W37 docket for the alpha glucosidase, 1B2I for the alpha amylase, and we get the dock score of all these. And this is the representation of that all, and here we have to get this all the data. This is also the superimposed resveratrol with that of the doxorubicin, the binding site of DNA polymerase second beta protein. So here what we see, because topoisomerase second is enzyme is responsible for the elongations of that chain. So what does T? So here what we have to dock within that topoisomerase second, they have to cleave this, they have to break down or cleave this. So by dock we can also say that our compound is cleave this chain. So there is no more chain elongation, no more making a hydrogen bonding with that anidine, guanine or thymine or cytosine. So this is the way by which we have to perform the dock of doxorubicin. So this is how it making the hydrogen bonding with the guanine, adenine, and here at the last in the beginning they have to cleave the chain. So now we also have to perform the docking studies of few molecule at the PPR gamma. So PPR gamma is just like a Y-shaped molecule. Y-shaped molecule means we have to design a molecule in such a way so our compound can accommodate with the Y shape of that molecule. So we have the arm 1, arm 2, arm 3. And there is an important thing which are available in the Schrodinger software that is called as the XP visualization. XP visualization, sometime the hydrophobicity or lipophilicity is important for what? To cross the membrane, because hydrophobicity is also required for the absorption of drug. So if your drug is hydrophobic, so it can easily cross the biological membrane and reach to the target site. Once your drug reach to the target site, what is next? Hydrophobicity is also important for drug receptor interaction according to Hans analysis or QSAR. So your drug must be hydrophobic enough to make a drug receptor interaction is there. So that's why in our molecule we have to put here the chlorophenyl group. And these CPK model, here these are the amino acid, this is a hydrophobic amino acid. So the orientation and pose of towards this hydrophobic they have. And this green part ball stick is the hydrophobic part of that molecule. So which are required for that of the cross this. Similarly here in case of naphthalene, this is the hydrophobic region, this part. And in XP visualization, we have to also showing the solvent exposed part. So by designing or lead optimize, because one thing which are recently I just understand that is one thing is called as the lead optimization. once we draw our lead molecule and immediately you press, you got the dock score and interaction. If your dock score is not up to that of the co-crystal ligand, so in that case you have to remove this part and you have to add some new part is there, and you have to add some functional group into the molecule. Again you have to produce and you get the score immediately within a second. This is the, I mean, within 2 or 3 days once we start the demonstration we can. So this is the best techniques by which we can have to generate our lead molecule and compare with that of the co-crystal molecule. So our aim is here what? So our lead molecule must have the high dock score, must have the good interaction as compared to that of the co-crystal ligand. Otherwise, what's the benefit of using this software? Nothing. So if you're not going to get the desired result or output, so means this part is the solvent exhaust, so you must have to remove this part. Similarly here in expo visualization we saw the rotable, how many rotable bond is there. And one thing is very important in Schrödinger software, that is called as the binding pocket by surface view model. So all the DPP4, they have the S1 pocket or the S1 pocket, or here we can say that S2 pocket or extensive. So this is the binding pocket of that S2 pocket. This is the extensive pocket for enhanced activity. So this paper is published in current topic of medicinal chemistry this year. I'm just taking one of these figures. And this is the binding pocket of the surface view of model of chicoic acid. So this is the binding pocket of the alpha glucosidase. So alpha glucosidase binding pocket is very large. Sir is sitting here. Once he came for interview of my PhD, selection committee. Actually, Professor Nasimul Huda come in Jamia Hamdard for selection committee. He asked why you have taken the alpha glucosidase for your design molecule. At that time, Alhamdulillah, I was able to answer it because our binding pocket is very large. So that's why we have to make a large molecule so that they can occupy the subsite 1 plus subsite 2 plus or minus subsite. So that's why I'm right, sir? What you asked and I said. So if your molecule is very small for alpha glucosidase, what? They have to only bind with the +1 subset. This part is not occupied. So in that case, the molecule is having the weak binding affinity. Your activity is dropped down. So that's why, first of all, we have to study the binding areas of that pocket of particular enzyme. So what are that area? What are that binding pocket? This, that. So this is also way we have to perform the binding energies of here the GABA way. So you can see these 1, 2, 3, 4, 5, 6, 7, 8 conformer is there, and they have the different binding energies. So we have taken the top one, which you can see there's the more favorable. In some part here, this molecule is out of this binding. This is the out of, and here this is also out. So out of these, which one is having the good affinity and the good binding energy is taken for the dock. So after performing the docking, what is the difference between dynamics and docking? Anyone can explain? Why we have to perform the molecular dynamics? Any idea? That can also by dock. Dock is also giving the. In molecular dynamics, we have to find out the stability of the molecule. Stability means what? So once we see the interaction between the receptor, but you never know how long this interaction can retain. How long your molecule get actually interacted with the receptor, whether 200 nanosecond or 100 nanosecond. For that, we have to perform the molecular dynamic. In case of molecular dynamic, atom level. So we have to put certain condition of the temperature, we can put certain movement, and we just allow to molecule for run. And here we have to find out the root mean square deviation, RMSD of ligand, RMSD of the protein, because we know that some part of the protein are flexible, some part of the protein are rigid in nature. So in some part of the molecules, root mean square fluctuation of ligand, some of the functional group of ligand is more fluctual. By lead optimization, we can replace so that it gets stable within the binding site or binding pockets of that receptor. So during the lead optimization by molecular dynamic, we can also replace our particular pharmacophore, a particular part of the molecule which can be changed so that to get better stability within the binding sites. So in molecular dynamics, what we see here, so this is the this paper is actually published in March 2025. We have taken here design the Jack kinase 3. So here this one is the root mean square deviation of that of the here, that is the protein. So in case of what we have to see, can you understand this image? What you have to observe in root mean square deviation of anyone? Eh? Catches who is saying? Raise the hand. What do you? So how can you have to this type? Because these two lines are going parallel to each other. So in case of RMSD, we have taken from here. If your ligand is going beyond 3 angstrom, so we have to consider the stability between the RMSD should be root mean square deviation should be from 1 to 3 angstrom. If your RMSD going beyond 3 angstrom like 4 or 5 means so that means what? Your ligand is not stable in the protein binding site. So in dynamics we have to see the बोल तो नहीं हो रहा.
Very interesting, but interesting for a particular area.
Interesting, and even I am learning a lot.
सबसे हमने सीखा. सर इज द मेंबर ऑफ आवर 3 PhD स्कॉलर SRC कमेटी. तो वो जाते हैं तो सर ही बताते हैं कि यहाँ पे ये करो, यहाँ पे ऐसे करो. सो आई एम स्टिल लर्निंग, आई एम स्टिल फील स्टूडेंट. जी सर. So whenever he went to Jamia Hamza, he always motivated me as well as my scholar. So they are waiting when Naseem sir is coming, when Rais sir is coming. So they are always giving the valuable inputs to our scholars and as well as the supervisor. So I can learn and impose in that our own research areas. So what I am saying, in a case of RMSD, your RMSD must be 1 to 3. If your RMSD beyond 3 means 4, 5, so means what? Ligand is losing the grip from the protein. So that means your interaction is not stable with that of the protein. So in that case, so we have to check the stability of RMSD and we have to run our dot complex in the dynamic Desmond in the Schrodinger. This is the free. Desmond is free in the Schrodinger. So we can, but for this you need to have the high graphics card and high 10 lakh or 12 lakhs of the system is there to run the dynamic systems. So here you can see these two lines are parallel. So and here 1 and 3, that is in between. So we can say our ligand is stable with that of the protein. Similarly here with that we have to compare with that of the co-crystal. How we have to compare with that co-crystal? Because whenever we have to perform the activity of our own design molecule, we always have to compare with the standard. So similarly here in dynamics, we must have to take one standard, that is the co-crystal ligands of that particular target site. And you can say the RMSD is also within 1 to 3 angstrom. So means ligand have the strong stability with that of the protein. And here this one is called as the root mean square fluctuation. Already I said that in case of protein, there the beta sheet, the flexible part, rigid part is there. So these long fluctuation peaks, they can show the more flexibility in the protein because we have taken a residue between 814 to 1064. This is the area where actually the molecule is actually binding. So this is the co-crystal fluctuation. And after that, here, what happened? We get the 2D leak plots by dynamics. So in here, before that, one picture, so I can show you. This is our design molecule, JAK3 kinase inhibitor. So here also the JAK3, leucine, and leucine 905 is the hinge region amino acid, proline, arginine, and this is the co-crystal ligand of that. Here is the leucine 905 pattern. So now this is the dock interaction, but we have to check by the dynamics whether these interactions are stable with the protein or receptor or not, JAK kinase. So for that we have to perform the dynamics. So in that case, we have to see the 2D structures of leak plot. So here you can see that leucine is 905. How much interaction is there? 97%. So means here there is a strong interaction with that. Suppose I just take a bus from here and just go to a Purani Delhi and just I'm standing and holding my hand with the roof of that bus, and during that journey the bus is moving here and there. So sometime what happened? And the duration of that journey is 1 hour by the bus from here to New Delhi or Purani Delhi. So during the journey and during the movement, some part of my whole hand is not properly holding. Sometime I just lose the grip from that roof. Sometime my feet is not stable here. So during the journey, I can say I strongly hold up this hand throughout the journey, or for a second. So we can say 90% holding, we can say 30%, 40%, or 50%. So these are the point where our molecule is interacting with the binding. So similarly in dynamics, what we see, we run our molecule for 200 nanosecond or 100 nanosecond for showing their stability of that molecule. So you can see by dock, the hydrogen bonding was already observed in case of previous dock image, leucine, and there here in case of docking we have to not remove all the water molecule, but in case of dynamics we can retain all these water molecule. So these are the proline 20%, aspartic acid 11%, arginine 24, this, and this is the co-crystal also, leucine 94. So after that, there is one fraction is there that is called as the interaction fraction. So these all are the amino acids. So we can take only interaction those above than 30%. We can take the interaction, yeah, hydrogen bonding, yeah, pi cation. If the interaction is more than 30%, we can keep all these. So here, out of these, leucine 900. So here they just the green line, they have to make a hydrogen bonding. This so the hydrogen bonding. This violet is that the hydrophobic, and this is the ionic interaction is there. So leucine 905, that is how much is around 90 to 97% is there. Similarly with that co-crystal ligand, that is the leucine is 905. So by molecular dynamics, we can perform the dynamic by atom level. How the atoms, how the amino acid is actually going to. But in case of dock, we cannot see that how much ligand is bind, 20%, 30% or 90%, whether your ligand is having a strong interaction with the receptor or not. So that is actually we have to check the stability by the RMSD of the ligand or by the RMSD of the protein. So, okay, thank you. So when I send our scholar, so he will giving you the demo of 3 to 4 hours here with help of the ESL. So you can understand the whole, because this is all about your passion. Docking and dynamics is nothing, because I believe that is the wet lab is very important. This is the part-time job. You can say you don't fully believe on that what goes, but this is all looks beautiful. If I'm wearing good clothes, so I look appear better. So that's called as the docking. So you cannot believe or rely only on the docking or the, but wet lab study is very important.
So no question from audience. Any question from audience? So today is second day and second lecture. Daily, you need to ask something. Yeah. Sir.
My question is like, sir.
Vikrant ji. Uzair sir. You need to ask.
Yes, sir. Sir, I do have a question. Like, malnutrition is one of the challenge and concern of our country. Like, the fraud marketing of like antioxidants in this food, that food. Like, I'm from Kerala and we are rich in green tea. Like tea plantations are there. And 1 day ago, like I have read one article, like green tea have many antioxidants. It was a biggest fraud marketing.
Polyphenolic compound is there, so that's
yeah, but like the hype was too high, and many of the middle class and the people who purchasing green tea, it was a little bit expensive, and but the actual studies came like this is not that much like proven, like green tea have that much effect on our like anti-cancerous, like that. Do the study and research in this area like molecular docking can do break the this fraud marketing in many food items?
Yeah, you really ask a good question. Because we have seen like quercetin, like resveratrol, these all are the, or coumarin country, these all are the polyphenolic compound, apigenin, epigallo, because tea having the extract that is called as the ECGC, epigallocatechin gallate. This is the tea extract, which have, even if you go through the literature, these molecule having the antioxidant properties by in modulating the dismutase oxidase by modulating the catalase, which convert the free radical oxygen dication into hydrogen peroxide, and hydrogen peroxide is converted into water and oxygen by catalase by modulating activity. So you can, and even resveratrol, already this is the polyphenolic compound, so they can be identified good for the cancer, good for diabetes, good for Alzheimer's, Parkinson's. A lot of research work is already been done on how, and how can you say that there is no any work is that? So there's a lot of work is going on in that area. So they claim, I mean,
It have studies saying it don't have that much effect like on like anti-cancer properties. Some articles are saying like that. So this research will help, right?
Sure, definitely it can help, because there is an area one called as the nutraceuticals. In nutraceutical, they all have to perform their bioactivities of all these polyphenols, coumarin, epicatechin, gallows, catechins, and that coumarin, quercetin. They all have to be going to perform. There are a lot of area is there. So okay. So, but the thing is that in that area is a lot of adulteration, because in the marketing they are just create a hype. So these formulation having the high of these antioxidant, but these the, because might be they are not going to extract the when purest form of that, and they are not going to make a formulation of purest of resveratrol, purest of all that. So that's the why you don't have to extract out the pure form yourself in the lab. So, and you can make a formulation and you can sell out. So you can, I mean, build up your own ideas to develop. I mean, you maybe one day you can be the millionaire. Okay, thank you.
Okay. Today lecture delivered by the Professor Uzair Alam is very informative, very valuable, and very learning. So thank you very much, Uzair sir. So now it is a time of felicitation. So I would like to invite Professor Kamrul Hassan sir from the Civil Engineering Department, accompanying the Nasim Loda sir. And please felicitate, and Nahid Nishad ma'am, please come and felicitate Uzair sir. Please come. Thank you. उधर से इधर ही आ जाइए निकाल के दे
सर यहाँ आ जाए ज्यादा अच्छा है, फोटो ज्यादा अच्छा है।
Thank you. So जैसे सर ने अभी बताया we are do further process. I mean, sir will send his scholar to hands-on the experiment. So we will arrange the time means after lecture. जो भी हमारा tutorials में आएगा उसमें हम 1 or 2 or 3 hours का means we will arrange the slot for hands-on learning. Okay, so thank you, sir.
And one more thing is that I will share my email ID with sir and my contact number. Whenever you design something and you need my help for designing your own way of work, so you can don't hesitate to ask me or don't hesitate to mail me. I am ready to help each of you individually, or I can assign one of my scholar. They can give you the additional demonstration and hands-on on weekend. Or weekdays or weekend basis, so you can understand. So it's all about your passion and your enthusiasm to learn. It's not possible. Everything is possible. Thank you.
So it is very good to do such work because sir has the means licensed software, not pirated. Therefore, the results will be obtained as accurate. Okay, so we will proceed this. Okay, thank you very much. So now we will go for lunch and assemble again at 2 o'clock, and then for further third lecture. Okay, bye. Thank you.
Everyone, and we are back again after the lunch session, and we again have our Professor Zain with us for some interesting topics. Like before pre-lunch session, we have an elaborative discussion about the mechanism of heterogeneous catalysis, and in this session, Professor Zain would be talking on the mechanistic part of those heterogeneous catalytic reactions. I hope you will have an enriching and interactive session. So over to you, sir. Thank you so
Thank you
much.
much. Thank you. Assalamu alaikum. Shall we start? Assalamu alaikum. Actually, in last 3 lectures, we talked. The first one was about introduction about catalysis, and we know that there is 2 types of catalysis, main 2 types of catalysis, which is homogeneous and heterogeneous catalysis. And we discussed also today about adsorption. And catalysis and adsorption are like 2 faces of the same coin. It means no catalysis without adsorption. I mean no heterogeneous catalysis without adsorption. Of course, you know that to make adsorption, we have 2 parts of adsorption, as we discussed at morning. We discussed at morning that adsorption may be chemical or physical adsorption. And what do you think in the case of heterogeneous catalysis? Will it be chemical adsorption or physical adsorption? I think your answer will be, it will be chemical adsorption. It should end at chemical adsorption. Of course, here, so whenever you hear about heterogeneous catalysis, you have to know that the first step of heterogeneous catalysis should be adsorption process. They are related together. And the adsorption may be physical or chemical, as we just mentioned that morning. What are the steps of heterogeneous catalysis? Here I'll try to imagine something. If you are from Mumbai, for example, and you came here to attend GIAN course, what will you do? You would just take a train or airplane from Mumbai until to come to Delhi or New Delhi. After that, you will take a taxi from airport to this university. At this time, you will prestigiously sit down and we will talk and discuss and react. After we finish, we will say goodbye, bye-bye. But your coming is different from your going because you came with some knowledge and you will leave with another knowledge. This is a reaction. After that, you will take the same taxi that you took first time, but from university to airport or train station. After that, you take the train and return back. This is the same cycle that mechanism takes. Because if you have a reactor and the catalyst is there, so the reactants move, diffuse to the region of the reaction of the catalyst. Then inside the pore, it travels to the active sites, and on the active sites they are reacting together. After that, product will be formed. Then product start to leave. And of course, I'd like to tell you that if the product love or like or have high affinity with the catalyst, that means, do you think it will be good catalyst and it will make good reaction, or it will not be good reaction? It will not be a good reaction because of the affinity should be medium. Here you can see that this is A from very far and the external diffusion, then internal diffusion. So it goes to the surface where reaction will occur. This reaction occurs to form the product, and then desorption starts to the B product will leave, and internal diffusion and so on to his home after returning back, and with a change in the reactants to product. This is a general scheme. We can summarize this scheme by this: diffusion of reactants gases to outer the sphere, internal diffusion of reactants in the pores, absorption of the reacting gases on the surface, and number 4, activation and reaction on the surface and the formation of the products. After the diffusion of products out of the surface, then internal diffusion and external diffusion for desorption. This is the main idea of mechanism of catalysis. I mean, adsorption process and desorption process. But if you have, of course, in heterogeneous catalysis, we have some possibilities. The first possibility is if you have one reactant, the other if you have two reactants or more. Let's have a look at if it is unimolecular reaction. This means this molecule or this reactant should or must be absorbed to complete the reaction. This is if it is unimolecular reaction, means only one reactant goes. Of course, you know, if it is unimolecular, so Langemeyer adsorption occur. And this is, I think we discussed at morning, it is chemical adsorption. After adsorption of this reactant, it will make a reaction. And let's go to if it is bimolecular, so it have many possibilities, like Langemeyer-Hinshelwood kinetics or Ehlers-Danlos kinetics or Mars kinetics. These are two are mean. Langemeyer-Hinshelwood and the Ehlers-Danlos are completely different, but Mars is very close to Ehlers-Danlos mechanism. There is a fourth one, but we will not discuss about it today. This is according to unimolecular or bimolecular. Let me ask a very small question. Do you remember what is rate determining step? If please try to, for next lecture, inshallah, try to read what's rate determining step because we may need it, inshallah. What about if it is unimolecular reaction? Of course, we will follow Langemeyer-Hinchelwood mechanism. As you remember, we discussed about what's Langemeyer-Hinchelwood at morning, and this is a new equation we can describe here. Rate of adsorption equals the D of Ca, the concentration of the change of concentration of reactant A over dt, which is time. Kt, that's equal Kt multiplied by theta. And of course, you remember what is theta. Theta is the coverage of the reactant. Equals Kt by this term, Ba multiplied by Pa over this term. I think you know these definitions. Ra is the rate of disappearance of A. Kt is the constant at any temperature. B is a constant. You remember at morning that it has K1 over K2, something like this. This one, if we have a reaction at two temperatures, what will happen? Here is the reaction at two temperatures, T2 and T1. Of course, the rate of T2, which is higher than T1, the rate at T2 is much bigger than T1 because T2 is higher than T1. And we mentioned before that the increase of temperature follows or is followed by an increase in the rate of reaction. I think it is 10 degrees of increasing temperature leads to an increase of chemical rate of equation rate with twice. It will be twice after 10 degrees. Of course, this is in a range of reaction conditions. If we change the range of temperature, of course, this will change. At the beginning, at low PA, you can see here that at low pressure, each curve approximates at straight line. All of these are straight line and follows the first order related to BA. At low P, in this equation, if you can see, RA equals Kt by BP over 1. If low P, this is if it is both are adsorbed. This means it is Langemeyer-Hinchelwood. Of course, you know, there is a very big question. Why do we use or why do we study mechanism? If you understand how the catalyst proceed, then you can increase it or decrease it or control it. You can do whatever you want if you monitor how it's. If you know how anybody will think, then you can control this one. If you don't know, so you are blind. Here you know how is the reaction thinking, or how is the mechanism, means how the reaction thinking, where it goes. This means you can study and control, increase or decrease, whatever. This is a reaction of H2O formation, H2 plus oxygen reaction. This was in Illyridai. Also the formation of NH3, it is Langemeyer-Hinchelwood. Both are Langemeyer-Hinchelwood. The other, this is, of course, we can follow the same in homogeneous catalysis. But let's see, this is an example. 2-methyl heptane will be adsorbed on the surface, occupied site, like with fraction of adsorption theta, and it goes to formation of B, which is the product, and the product desorbed out of the surface. After that, you will have the surface clean again, so another cycle will happen. This is a model or an example of bimolecular reaction. For Illyridiol, the case is different. For Illyridiol, what happens? Very, very simple. What happens? For Illyridiol, if one of the two reactants will be adsorbed, after that, the other reactant is reacting with this reaction with the adsorbed reactant from far away. It's like what if you go to your room and you find your brother or your sister just catching a electric wire, and he is shaking like this. What will you do? You just hold him, right, to save him. If you hold him to save him, what will happen? You will be electrified as well. So this is the case. If A will be absorbed on this on the active side, absorption, so B will go and interact with A like this. So after that, it forms product. So B itself is not absorbed on the surface, but it forms with interaction with A, it forms a product P. After formation of product, desorption will occur and the B will leave the surface. The surface is empty again, so A and B started to be to absorb again, and consequently or continuously the reaction. Okay. Now there is a big question will arise, which is how can we differentiate between Ehlers-Danlos and Langemeyer-Hinshelwood mechanism? How can we differentiate it? How can I know, or how can I decide this reaction proceed in Langemeyer or Ehlers-Danlos mechanism? It's very simple. Of course, this is two reactant. If all the reactants are adsorbed, this means Langemeyer. And if one of the reactants is adsorbed only, this is Ehlers-Danlos. So the question is, how can we distinguish between the two mechanisms? How can we distinguish between the two mechanisms? How can we decide if this reaction goes through Langemeyer-Hinshelwood or Ehlers-Danlos? Okay. This is in this case the reaction. Both reactants are going to the surface. If the rate increases with the presence of two reactants on the surface, if the rate increases, this means this is Langemeyer-Hinshelwood. But in this case, if the reaction increases in this while only one reactant on the surface, then it follows Ehlers-Danlos mechanism. But if the reaction will die, or the rate of reaction, the rate constant will be zero in the upper case, this means it should be Langemeyer-Hinshelwood mechanism. I think it's clear. If you have two reactants, A plus B, you will just make a monolayer of A, for example. If the reaction will stop, if the reaction will die after full coverage of A, this means it needed, or B should be on the surface as well to processing for processing the reaction. If it goes very smooth and very happy, this means it doesn't need B on the surface, then it is Ehlers-Danlos mechanism. I think it's clear, right? Again. In other words, if Ehlers-Danlos, this we make full coverage of the surface, coverage with A. If the surface is covered completely with A, and the reaction rate increases by increasing the coverage until coverage theta equals 1, this means it didn't need B on the surface. This means it needed only A on the surface. Ehlers-Danlos mechanism. Okay? But if the reaction increases by time until medium of coverage, then the rate goes down again to 0 at complete coverage. This means it needed both of the reactants on the surface, and I just removed one of them, so the reaction will not proceed. Is it clear? I think so. The last one is, and of course, here I just remember something I want to just tell you. Now I control the reaction. If I can control the reaction, like if I give it A only or B only, will it be different? Will it be different or not? So it may have A only and work. B will interact with A from outside. But if I give it B, will A interact with B from outside or not? So the reaction may decide he needs only one, yes, but which one? You don't understand. Okay. I mean, there is another question I didn't answer here, which is the reaction may need only one, and we answered that if it needs only one reactant, it will go through Ehlers-Danlos mechanism. But which one it will need? Will it need A on the surface or B on the surface? This is another big question. So we will skip it today. If you can think about it, we can answer it later on. Okay? Which reactant it should be there on the surface? Now, the last one, or before last, but we will talk about is Mars van Krevlin mechanism. What is this? It is very similar to Ehlers-Danlos mechanism, where it is like this. This is A. It is a part of the catalyst, itself. B comes and react with A, like Ehlers-Danlos. That's why I told you it's similar to Ehlers-Danlos. B comes and react with A from outside like this. It's absorption of B over A and reacts like this, and the P is formed, then desorbed, B desorbed from here, and once B desorbed, it leaves vacant space. This vacant space will be, of course, consummate by adding another A from outside, from the reactants. Another A from the reactants to fulfill the surface of the catalyst and again the cycle. Clear? The difference here between, there is tiny difference between Ehlers-Danlos and Mars. What is the difference? The catalyst is working from its structure and devote some atoms to the reaction, which fulfills the reaction and then consummate it again from the medium or from reactants itself. We can see, but in the other case, in Ehlers-Danlos, the case is different. Why? The case was A plus B are absorbent, will be absorbed on the surface. A is going to the surface, and B will interact with A from outside. But here, A is a part of the structure. This is the difference between Mars and Ehlers-Danlos. This is an example. This is just I added here like equations. B will go to A on the surface. It gives transition state BA. After that, the transition state will form C, which is the product. After that, the C will leave the surface. Then it consummates S. Surface will consummate the missed atom, which is A, from the medium, and forms AS again, which we already started with this structure. It is like we will introduce this example. I think you will. It will be clear. Like this. It is O is there in the structure. CO comes and react with O like this to form CO2. Then CO2 will leave the surface and return, and the previous structure return back without O, which takes O from the medium and forms the original structure. This is Mars mechanism. It is like oxidation of CO with oxygen. CO with like this example. If we have platinum oxide, of course, platinum oxide structure has platinum and oxygen on the on the surface or on the structure. After that, CH4 comes to be CH4 will come and forms two bonds HO and CH3 platinum bonds, and then oxidation methanol will be formed and leaves the structure like this, forms and platinum oxide return back and it takes oxygen from the medium and reaction complete. I think we finished the possibilities of the mechanism in heterogeneous catalysis today, and I hope it's clear. If anybody has any question, I am here. Let's go. Thank you very much. Any question? Thank you. شكرا. السلام عليكم.